Imagine a world so much like Earth that, for a while, some of the smartest people alive thought it could be a paradise of alien jungles and warm, misty oceans. A world wrapped in bright white clouds that refuse to let you see what is really happening below. A world that turned out not to be a second Eden, but a furnace where metal softens, rocks glow with heat, and the air itself crushes anything that dares to touch the ground. That world is Venus. Earth's twin in size and mass, but a twin that somehow went terribly, catastrophically wrong. For most of human history, Venus has been nothing more than a bright wandering star in the sky, a shimmering beacon just before sunrise or after sunset. Yet, in the middle of the 20th century, it became something else. A target, a mystery, and eventually a graveyard for some of the most ambitious machines ever built. This is the story of what happened when humanity finally decided to punch through those clouds and land on the most hostile surface in the inner solar system. It is the story of a long, stubborn, almost obsessive campaign led by the Soviet Union to touch a world that did not want to be touched. Again and again, they launched into the unknown, losing spacecraft to heat, pressure, and the brutal physics of another planet. And yet they kept going, chasing a handful of hours of data, a few blurry pictures, and the right to say, "We were there." What they found beneath the clouds was not the lush, steaming rainforest that some had imagined. Instead, they discovered a hellscape, temperatures hot enough to melt lead, pressures like being buried beneath an ocean of air, and an atmosphere laced with corrosive chemicals. But the way they discovered it step by step, failure by failure, probe by probe, is a saga of human ingenuity pushed to its limits, unfolding against the backdrop of the Cold War and the race for prestige in space. In the early days of the space age, Mars was not the star of the show. Venus held the spotlight. From Earth, astronomers could peer at Mars and see hints of its surface, dark patches, bright polar caps, the suggestion of a real landscape. Venus was different. No matter how powerful the telescope, the planet stayed smooth and blinding, smothered in a permanent blanket of bright clouds. The surface was invisible, and that made it irresistible. Those clouds hinted at something intriguing. A thick permanent cover meant a substantial atmosphere, more like Earth's than the thin whisper of air around Mars. Venus orbits closer to the Sun. So many scientists reasoned that the surface might be warm, humid, and dynamic. For a time, in serious discussions and popular imagination alike, Venus could plausibly be a greenhouse world of swamps and jungles, its skies heavy with rain, its land populated by strange plants and hardy alien animals. By the middle of the 20th century, the image of a wild, tropical Venus was already under pressure from a different idea. Some researchers, most famously among them Carl Sagan, argued that the permanent clouds might be the sign of a runaway greenhouse effect, not a gentle warm fog. In this picture, Venus was not a steamy paradise, it was an oven. Thick carbon dioxide, an intense blanket of infrared trapping gas, could cook the surface to incredible temperatures. If that were true, then beneath the clouds there would be no jungles, only a scorched wasteland. But from Earth, there was no way to be sure. Telescopes could only see the top of the cloud deck, not what lay beneath. The only way to settle the debate was to send machines across tens of millions of kilometers of space, through the glare of the sun, and into the orbit of a planet that had never been visited. The timing of this question could not have been more dramatic. The 1,950 seconds and 60 seconds were the era of the Cold War, when the United States and the Soviet Union turned spaceflight into a showcase of ideology and technological power. Getting into orbit was not just a scientific achievement, it was a symbol, a message. We can build rockets that reach beyond Earth, and that means we can build rockets that can reach anywhere. The Soviet Union leapt ahead early. They launched the first artificial satellite, Sputnik, shocking the world with a beeping metal sphere that circled the planet. They sent the first human, Yuri Gagarin, into space, proving that a person could survive an orbital flight and return alive. They crashed the first human-made object into the moon, marking it with a silent, invisible bruise of metal and dust. Each milestone was a statement, a demonstration of capability and ambition. In that climate, Venus stood as the next logical target. It was the closest planet beyond the moon, and because of its thick atmosphere and cloud cover, arguably the most mysterious. Sending a spacecraft there would not only answer a scientific puzzle, it would secure another first for whoever got there before the other side. The Soviet leadership saw an opportunity. If they could be the first to reach, study, and perhaps even land on Venus, they would add another triumph to a growing list of space firsts. Yet this was not simple exploration. Computers were crude by modern standards, guidance systems were limited, and the behavior of interplanetary spaceflight was still being learned through trial and painful error. To hit a target as small as a planet across such vast distances, engineers had to use careful calculations, raw intuition, and machines that were, by today's measure, barely more than metal shells packed with radios and simple electronics. Still, they tried. They built a pair of spacecraft and gave them a name that would become legendary in the history of planetary exploration. Venera, Venera 1, and Venera 2 were bold and fragile. Launched in the early 1960 seconds, they carried instruments designed to measure the environment around Venus and, if possible, learn something about its atmosphere and surface. They were not capable of landing yet. Just getting a spacecraft to fly past the planet and send data home would be a victory. The launch procedure itself was daring. Engineers placed these probes atop powerful rockets originally developed as ballistic missiles, strapped on an upper stage to push them out of Earth's gravity well and aim them toward a moving target that would be in the right place in space months later. Once the trajectory was set, there was little room for adjustments. The spacecraft would coast through the void thousands of kilometers per hour with limited ability to correct course or fix problems. Both Venera 1 and 2 did something remarkable. They reached the vicinity of Venus. Their flight paths carried them within roughly 100,000 kilometers of the planet, a small miss on cosmic scales, close enough to sense the pull of its gravity. But both probes suffered catastrophic failures before they could gather useful information. Their systems shut down, their radios went silent, and they floated past in darkness, unable to tell their makers anything about the world they were built to investigate. From the outside, these missions could be seen as failures. No measurements, no images, no dramatic discoveries. Yet for the Soviet engineers, they were stepping stones. The probes had reached interplanetary space, survived part of the journey, and proven that trajectories to Venus could be calculated and executed. Now they had data about what went wrong and time to try again. Meanwhile, on the other side of the Earth, the United States prepared its own robotic ambassador to Venus, Mariner 2. In 1962, Mariner 2 flew past Venus and completed the first successful close-up study of another planet in human history. For over 40 minutes, it scanned the planet, measuring the radiation coming from its atmosphere. The results shattered any remaining hope that Venus might be a warm, wet cousin of Earth. The data suggested that the surface was staggeringly hot, with temperatures high enough to double the boiling point of water. This was exactly what the greenhouse model had predicted. Thick layers of cloud and carbon dioxide were not gently trapping warmth. They were locking in so much heat that the surface became a global kiln. Above that inferno, clouds towered to altitudes that, on Earth, would graze the edge of space. From those numbers alone, one could infer that no familiar life could survive on such a world. Machines would barely last. Any lander that touched the surface would have to endure heat far beyond what typical electronics could survive, and pressure so intense that it would crush most structures as if they were made of paper. The reaction in the United States was pragmatic. If Venus was effectively a planetary furnace, then sending delicate and expensive hardware to its surface did not look like a wise investment. Mars, with its visible surface and more moderate conditions, appeared to be a better bet. The Moon, too, was an obvious target. It was close, reachable, and symbolically powerful. So attention shifted. Stepping on the lunar surface and rolling across the Martian plains became more appealing than plunging into a toxic, burning atmosphere. The Soviet Union, however, made a different calculation. To them, the harshness of Venus was not a deterrent. It was a challenge. If they could tame this world long enough for a lander to function, if only for an hour, they would achieve something no one else had. The more hostile Venus appeared, the more unique the prize of conquering it became. By the mid-1960 seconds, the Soviet space program had evolved. Experience with lunar and planetary flights had taught hard lessons about navigation, communication, and the fragility of hardware in space. When they returned to the idea of visiting Venus, they did so with heavier, more capable spacecraft. The next generation of Venera probes, launched in the latter half of the decade, were bigger and tougher than their predecessors. Their mass climbed to nearly a metric ton, packed with instruments to measure temperature, pressure, atmospheric composition, and more. Most importantly, each carried a separate descent module, a sealed pod designed to detach from the main spacecraft, plunge into the Venusian atmosphere, and transmit data as it fell. These descent capsules were equipped with barometers, thermometers, gas analyzers, and radar altimeters to determine altitude. They carried parachute systems to slow their fall, giving them more time to sample different atmospheric layers. The mission concept was elegant. The capsule would enter the atmosphere at high speed, deploy its parachutes as it slowed, and then drift downward, recording how conditions changed with depth. But Venus had surprises to offer. One early lander, sent in the mid-1960 seconds, suffered a total system failure on the way, yet its trajectory still intersected the planet. It slammed into the surface at high speed and became, unintentionally, the first human-made object ever to collide with another planet's ground. It did not send back data, but it marked another grim milestone in the struggle to explore this world. The next Venera descent capsules fared better, at least initially. One of them, entering Venus in the late 1960 seconds, managed to relay readings from within the atmosphere. As it drifted down, it experienced something fascinating and terrifying. At high altitudes, the air felt surprisingly familiar, temperatures and pressures not far from those in a warm, humid day on Earth. But with each kilometer of descent, the environment grew more extreme. The pressure rose relentlessly, the heat intensified. The deeper it fell, the more the air acted not like a gentle gas, but like a crushing ocean. The capsule's slow descent through this dense fluid was akin to diving into a planet made of hot air and acid. Eventually, after roughly an hour and a half, the transmission stopped. The prevailing interpretation was simple. The capsule had been crushed by the weight of the atmosphere before it ever reached the surface. This failure carried a brutal message. Venus's atmosphere at ground level was not just uncomfortable, it was annihilating. If the Soviet Union wanted a lander to survive all the way down and function on the ground, they would have to build something far stronger than anything that had gone before. By the end of the 1960 seconds, the United States had orbited astronauts around the moon and was on the verge of landing humans on its surface. The Soviet leadership knew they were unlikely to match that specific feat, but they could still stake out new territory in robotic exploration, and Venus was their chosen frontier. Despite the grim fate of earlier capsules, they launched more Venera probes, again sending them into the choking clouds. Two landers with similar designs plunged into the atmosphere in quick succession. Both relayed measurements for less than an hour before becoming silent, probably crushed like their predecessor. Each mission proved that the pressure and temperature near the surface were every bit as brutal as feared. Yet the pattern of failure did not break the program. Instead, it pushed Soviet engineers toward more radical design changes. If the atmosphere could crush their capsules, they would make the shells thicker. If the heat could cook their electronics, they would wrap them in insulated layers and build internal pressure vessels, like miniature deep-sea submersibles. The next wave of Venera landers incorporated major structural upgrades. The descent module's outer hulls were built from stronger materials, and inside those shells, the instruments were enclosed in spherical pressure vessels made of titanium or similar robust metals. Additional shock absorbers and padding helped the lander survive not only the crushing air, but also the final impact with the rocky surface. These reinforced capsules were not subtle. They were heavy, blunt, and built with one priority: endurance. The goal was no longer just to sample the atmosphere as they fell. The engineers wanted them to smash into the ground, survive the landing, and continue transmitting for at least a short time. If they could do that, they could finally see and measure the surface of Venus directly. When one such lander descended into the thick air in 1970, something unexpected happened. Its parachute did not function properly. Whether it tore, melted, or failed to deploy as designed, the result was the same. The lander fell much faster than planned. It hit the surface at a speed that would have destroyed any previous design. But this time, the capsule did not die. It struck the ground, bounced, and kept working. Through a battered antenna and stressed hardware, it managed to send back data from the surface itself. The readings were sobering. Temperatures hovered around hundreds of degrees Celsius, hotter than the inside of a typical household oven, hot enough to make most metals glow dark red. The pressure was dozens of times that at sea level on Earth, equivalent to being a kilometer underwater in a terrestrial ocean. Venus, it turned out, was not a warm cousin of Earth. It was a crushing, searing world where the concept of weather meant endless heat and suffocating air. Yet, the Soviet Union had done something extraordinary. They had put a machine on the surface of this nightmare planet and made it talk. In the 1,970 seconds, as the Soviet Venus campaign evolved, the focus of the broader space race shifted. The United States had already walked on the moon, planting flags and leaving footprints in the dust. The Soviet Union, recognizing that they would not beat that milestone, chose to expand their robotic exploration in other directions too. They sent probes to Mars, achieving the first soft landing on its surface. Even though that lander lived only seconds before falling silent, they deployed orbiters around other planets, gradually building a web of firsts in robotic planetary exploration. In this landscape of shifting priorities, Venus remained a grim but enticing laboratory. One of the later Venera landers in the early 1,970 seconds managed something important, a relatively gentle landing and nearly an hour of operation on the surface. From that mission came refined measurements of surface pressure and temperature, confirming that the atmosphere pressed down with a force over 90 times greater than Earth's sea-level air. The lower atmosphere was loaded with corrosive compounds, including sulfuric acid droplets, chemistry more fitting for an industrial furnace than a peaceful landscape. Any one of these facts would make Venus hostile. Together, they painted a picture of an environment that actively destroys machinery. Electronics overheat, metals weaken, and seals degrade. It is a world where survival for any human hardware must be measured in minutes or hours, not days or years. For most space agencies, this would be a clear signal to stop. After all, there are other planets where rovers can roam for years, taking thousands of images and measurements. Why choose the one that breaks everything in a matter of hours? But the Soviet engineers and scientists saw something different. They saw proximity, scientific value, and a chance to secure a legacy. Venus is Earth's closest planetary neighbor in terms of size and position in the solar system. Understanding why it turned into a hellscape while Earth remained habitable is a fundamental question in planetary science and climate studies. The Soviets believed that pushing deeper into this hostile world could reveal clues about planetary evolution and perhaps even Earth's own future. And they knew one more thing. Despite the thick clouds, some light still filters to the surface. Enough, perhaps, for cameras. That possibility opened a new objective: not only measure, but see. If a lander could survive long enough to operate a camera, it could capture the first photographs ever taken from the surface of another planet. That idea had enormous power. A single image, even of a barren landscape, can transform an abstract idea into a tangible reality. Numbers tell scientists what the environment is like. Pictures show everyone what it feels like. The next generation of Venera landers was designed with that in mind. The spacecraft grew heavier, approaching the mass of a small car or even, at full configuration, the weight of a large animal. The descent module itself became a robust, squat structure, with a thick impact ring at its base to absorb the shock of landing. One of the most clever changes was in the landing strategy. Previous landers had relied on large parachutes to slow their descent, but the lower atmosphere of Venus is so thick it behaves more like a fluid than like the thin air we know. Instead of wrestling with parachutes that could tear or melt, engineers realized they could exploit the density of the atmosphere itself. They fitted the lander with an aerodynamic braking structure, a sort of broad hat that would increase drag in the upper atmosphere and slow the craft as it plunged downward. Combined with the incredible density of the lower layers, this would reduce the lander's speed to something survivable by the time it reached the surface. The thick air would do much of the work that parachutes did on other planets. The impact ring at the bottom, attached with shock-absorbing supports, acted like a giant circular landing gear. Its broad footprint and internal dampers allowed the capsule to hit the ground at significant speed without immediately cracking open. Around the ring, engineers added metal fins to stabilize the lander during descent, reducing spin and wobble so that the final touchdown would be less violent. Inside, cameras were nestled behind protective covers that would shield their lenses from the superheated acidic atmosphere during entry. Only after landing would these covers be commanded to open, exposing the optics to the environment just long enough to snap pictures and transmit them before the lander succumbed to the harsh conditions. Everything in these designs was a trade-off between robustness and time. The landers did not need to endure for months. They needed to survive atmospheric entry, landing, and perhaps an hour or two of operation. In that window, every second would matter. In the mid-1970 seconds, one of these upgraded Venera landers descended through the yellowish haze and came to rest on the surface of Venus. For the first time in history, a camera sat on the ground of another planet, ready to look around and send back its view. The images, captured on film and then scanned line by line for transmission back to Earth, were not dramatic in a cinematic sense. There were no towering mountains or sweeping vistas. Instead, the camera saw a field of fractured, blocky rocks scattered around the lander, surrounded by a coarse, granular surface that looked vaguely like sand or gravel. The horizon was low and close, distorted by the thick air and the limited field of view. The sky was not blue, but a bright, diffuse glow filtered through endless clouds. And yet, those pictures were extraordinary. They showed, in stark grayscale, a world that no human eye could ever see directly. They replaced imagination, lush jungles, or seas of lava with reality. A cracked, baked plain of rock under a dark, oppressive sky. A second lander, arriving days later at a different location, saw a smoother surface, likely solidified lava, with fewer rocks and a more uniform texture. Venus, like Earth, had a varied landscape, but one that had been shaped by extreme heat and volcanic activity. Later missions refined this visual record. One particularly successful lander in the early 1980 seconds delivered the first color images from the surface of Venus. Now the rocks and soil were not just shapes, but hues. Muted yellows and browns, tones of heated stone under a strange tinted sky. The lander had come down near a slope, allowing the camera to capture a suggestion of depth. A foreground of stones and structural elements, and beyond them, the gentle rise of terrain fading into the heavy air. Around the base of the lander in those images, one could see the hardware itself, the circular impact ring with its jagged teeth, the metal fins protruding outward, cables, and structural supports. The gear looked brutal and purposeful, like something designed not for elegance, but for survival in a place that wanted to destroy it. The mission did more than just take pictures. Some landers carried drills and soil analyzers, scraping the top layer of the Venusian surface and studying its composition. The rocks turned out to be broadly similar to volcanic materials found on Earth's solidified ash and basalt-like stone. This hinted that Venus, too, had experienced intense volcanic activity, building plains and flows of hardened lava. One lander even carried a microphone, allowing scientists to record sound from another planet. The audio was, on the surface, unremarkable. Low wind, mechanical noises from the lander itself. But knowing that those whispers of air were moving through an atmosphere far denser and hotter than any place on Earth lent them an eerie, alien quality. It was the sound of a place where no human could stand and live, carried across space as vibrations encoded in radio waves. Each of these missions was fleeting. On Venus, electronics didn't simply fail, they were overwhelmed. As time passed, internal temperatures climbed. Critical components reached their limits and then exceeded them. After an hour or two, sometimes less, the landers fell silent. They became motionless relics on a distant, unforgiving surface, slowly baking and corroding in the eternal heat. By the time the last of these Soviet landers touched down, Venus had given up many of its secrets. Scientists had measured its crushing pressure, its toxic carbon dioxide-rich atmosphere, its lethal temperatures, and its volcanic surface. They had seen the ground, touched it, listened to its winds, and sampled its rocks. They had learned that this so-called twin of Earth had, through some divergence in its history, become a world where ordinary chemistry and planetary processes conspired to lock in catastrophic heat. Each mission represented enormous effort, years of design and testing, expensive rockets, and the risk of public failure if the hardware broke before it could deliver results. In contrast to missions to Mars, where rovers can roam for years and send back rich datasets, Venus landers offered only brief windows of operation. The best of them survived roughly 2 hours on the surface. Often, they delivered only minutes of data before succumbing. At the same time, the Soviet Union itself was changing. Economic strain, political shifts, and, eventually, the collapse of the state reshaped national priorities. Funding and focus drifted away from the costly, high-risk business of landing machines on a planet that destroyed them so quickly. Once those last Venera landers had fallen silent, no new missions followed to continue their work on the surface. Other space agencies, including NASA, were cautious. Orbiters and flyby missions to study Venus from a safer distance were more appealing providing longer-term scientific returns without the almost guaranteed destruction of expensive landers. Trying to justify the cost of sending hardware into an environment where survival is measured in minutes is difficult, especially when politicians and planners demand clear, long-term payoffs. And so, the surface of Venus became, once again, a quiet mystery. Not the mystery of ignorant scientists now knew the broad strokes of what it was like, but the mystery of inaccessibility. Humanity has small, precious glimpses of how it looks and feels, but no ongoing presence. The last images we have from the surface date back decades. The last landers to touch down there did so in a different political era, under a flag that no longer flies. Today, when people talk about the exploration of other worlds, Mars dominates the conversation. Rovers there climb hills, drill rocks, and stitch together panoramas of dusty plains. Moons like Europa and Enceladus inspire visions of subsurface oceans and potential life. Venus, despite being closer and more Earth-like in size, lingers in the background as the dangerous one, the world that punishes every attempt to visit. Yet the story of those Soviet missions to Venus is not just about danger and failure. It is about how far humans are willing to go to answer simple questions. What is this world really like? Why did it turn out so differently from our own? How does a planet that begins as a sibling of Earth become a furnace? Venus and Earth were born from the same cloud of dust and gas, spinning around a young sun roughly 4.5 billion years ago. They condensed from similar materials at similar times, sweeping up rock and metal as they grew. When the chaos of planetary formation settled, the two worlds emerged remarkably alike in size and mass. Venus is only slightly smaller, with a diameter about 95% that of Earth. Their internal structures, mantles of hot rock surrounding iron cores, follow the same basic blueprint. For a time, early in their histories, they may have been even more similar than they are now. Some scientists believe that young Venus could have possessed liquid water on its surface, oceans that collected in basins and shaped an early climate. The energy from the sun would have been slightly less intense billions of years ago, and if Venus had water and a moderate atmosphere, it might have looked almost Earth-like. Blue skies, clouds of water vapor, perhaps even rain. But something went catastrophically wrong. Over time, Venus transformed into the furnace we see today. Understanding that transformation is one of the deepest puzzles in planetary science, and the answer lies in a delicate balance of distance, chemistry, and feedback loops that can push a planet past the point of no return. The greenhouse effect is not inherently bad. On Earth, it is essential for life. Without it, our planet would be a frozen wasteland, too cold for liquid water to exist on the surface. Gases like carbon dioxide and water vapor in the atmosphere trap some of the sun's heat, warming the surface to temperatures where oceans can flow and life can flourish. Venus experienced the same basic process, but with a crucial difference. It sits closer to the sunday. That extra proximity means more solar energy striking the atmosphere and surface. Early in Venus's history, if liquid water existed, the added heat would have caused more of it to evaporate. Water vapor is itself a powerful greenhouse gas, so more evaporation led to more warming, which caused even more evaporation. This is the beginning of a feedback loop. As temperatures climbed, the oceans, if they were there, began to boil away. Water vapor filled the atmosphere, trapping more heat. At the same time, carbon dioxide, locked in rocks and perhaps dissolved in those early oceans, was released into the air. On Earth, carbon dioxide cycles between the atmosphere, oceans, and rocks, regulated by weathering, rain, and geological activity. But on Venus, with its water gone and temperatures soaring, there was no mechanism to pull the carbon dioxide back out. It accumulated. The atmosphere thickened. The pressure at the surface increased. More heat was trapped, driving temperatures even higher. This is what scientists call a runaway greenhouse effect, a process where each step amplifies the next, spiraling out of control until the planet reaches a new, extreme equilibrium. Venus locked itself into a state where the surface became hot enough to glow, where no liquid water could exist, and where the thick blanket of carbon dioxide ensured that the heat could never escape. Today, Venus's atmosphere is over 90 times denser than Earth's, composed almost entirely of carbon dioxide, with clouds of sulfuric acid drifting high above. The surface temperature hovers around 475 degrees Celsius, hotter than Mercury despite being farther from the sunday. The planet has become a cautionary tale, a world that started out with potential but crossed a threshold from which there was no return. Another difference between Earth and Venus deepens the mystery. Earth has a strong magnetic field, generated by the churning of molten iron in its outer core. This magnetic shield deflects much of the solar wind streams of charged particles flowing out from the sun and protects our atmosphere from being gradually stripped away. Venus has no such shield. Its magnetic field is negligible, possibly because its core cooled differently, or because its rotation is so slow that it cannot generate the dynamo effect needed to sustain a field. A day on Venus lasts longer than a Venusian year. The planet rotates so slowly that the sun rises in the west and sets in the east, and one full rotation takes more than 240 Earth days. Without a magnetic field, Venus is exposed to the full force of the solar wind. Over billions of years, this relentless bombardment has likely stripped away lighter elements from its atmosphere, including much of the hydrogen that once formed water molecules. If Venus ever had oceans, the hydrogen from that water may have been blown into space, leaving only oxygen to react with surface rocks. The water is gone, stolen by the sun and the lack of magnetic protection. This loss of water is not just a detail, it is a key part of why Venus cannot recover. Water is crucial for regulating climate, weathering rocks, and cycling carbon. Without it, there is no rain to wash carbon dioxide out of the air, no oceans to dissolve it, and no way to break the grip of the runaway greenhouse. Despite its hellish conditions, Venus is not geologically dead. The surface shows vast plains of solidified lava, enormous volcanic structures, and features that suggest the planet has been volcanically active in its relatively recent past. Some scientists believe that Venus may still have active volcanoes today, periodically erupting and adding fresh material to the surface. The plains of basaltic rock that the Venera landers sampled are the result of these volcanic processes. Unlike Earth, where tectonic plates shift and recycle the crust over time, Venus seems to lack the same kind of plate tectonics. Instead, it may resurface itself in catastrophic episodes, where the crust becomes so hot and unstable that large portions melt and flow, covering old terrain with fresh lava. This violent geology has erased most traces of ancient craters and surface features. The Venus we see today is, in a sense, young, perhaps only a few 100 million years old in terms of its surface age. Whatever history existed before has been buried beneath flows of molten rock, locked away beneath a surface that constantly bakes under an unforgiving sky. Volcanic activity also contributes to the atmosphere. Eruptions release gases, including sulfur compounds that form the sulfuric acid clouds high in the atmosphere. These clouds create the bright, reflective blanket that hides the surface from view, giving Venus its brilliant appearance in Earth's sky while concealing the inferno below. The story of Venus is not just about another planet's tragic fate. It is a mirror held up to Earth, showing what could happen if delicate balances tip too far. The mechanisms that drove Venus into a runaway greenhouse atmospheric composition, distance from the sun, loss of water, and volcanic outgassing are all factors that exist on Earth as well. Our planet sits in what scientists call the habitable zone, the range of distances from the sun where liquid water can exist on a surface. But that zone is not a hard boundary. It is a probability shaped by atmospheric chemistry, geological activity, and the presence of oceans and life. Earth has remained habitable for billions of years, not because it is immune to the processes that destroyed Venus, but because it has maintained a balance. Carbon cycles between air, water, and rock. Oceans regulate temperature. Life itself, through photosynthesis and other processes, plays a role in shaping the atmosphere. If that balance were disrupted by a large increase in greenhouse gases, by the loss of oceans, or by changes in solar output, Earth could begin a slide toward conditions more like Venus. The timescales might be different, and the triggers might vary, but the physics is the same. A thick atmosphere of carbon dioxide, unchecked by natural cycles, will trap heat. Rising temperatures will release more carbon dioxide from rocks and oceans, amplifying the effect. Feedback loops can push a system beyond recovery. Venus is a reminder that planets are not static. They evolve, sometimes in directions that are irreversible on human or even geological timescales. Understanding how and why Venus became what it is helps scientists refine models of planetary climate, informs the search for habitable worlds around other stars, and sharpens our awareness of the fragility of our own environment. Despite everything learned from the Venera missions and later orbital studies, Venus still holds mysteries. The exact history of its water is uncertain. Did it ever have oceans? Or was it always too hot for liquid water to persist? If it had water, how long did it last? And what triggered the final collapse into a runaway greenhouse? The slow rotation of Venus is another puzzle. Why does it spin so much more slowly than Earth and in the opposite direction? Some theories suggest a massive impact early in the planet's history, an event that could have knocked it into a retrograde spin and altered its rotation rate. But evidence for such an impact is hard to find, buried beneath a surface that has been reshaped by volcanic activity. There is also the question of current volcanic activity. Orbital missions have detected signs that might indicate recent eruptions, changes in atmospheric chemistry, bright spots on the surface that could be fresh lava. But without active landers or long-term surface observation, it is difficult to confirm whether Venus is still an active volcanic world or whether the signs are echoes of events that happened millions of years ago. The thick clouds themselves remain enigmatic. They are made of sulfuric acid droplets, but the exact processes that create and maintain them are not fully understood. High in the atmosphere, where temperatures are cooler, conditions are surprisingly Earth-like moderate pressure, temperatures where liquid water could exist. Some researchers have speculated, controversially, that microbial life could potentially survive in those clouds, floating in droplets and cycling through the atmosphere. There is no evidence for this, but the idea underscores how little is truly known about the full complexity of Venus's environment. For decades, Venus has been a world observed from a distance. Orbiters have mapped its surface using radar, piercing the clouds to reveal mountains, valleys, and vast volcanic plains. They have studied atmospheric dynamics, tracking winds that roar through the upper atmosphere at hundreds of kilometers per hour, creating a phenomenon called superrotation, where the air moves far faster than the planet itself rotates. But orbiters can only tell part of the story. To truly understand a world, you need to touch it, to measure its rocks directly, to feel the weight of its air and sample its chemistry in real time. That is what the Venera landers provided, and it is what has been missing ever since they fell silent. The reasons for this silence are practical. Building a lander that can survive on Venus is expensive and technically challenging. The return on investment, measured in operational time, is painfully short. Unlike Mars rovers that can operate for years, a Venus lander might function for an hour or two at best, even with the most advanced technology. For space agencies working with limited budgets, it is hard to justify such missions when other targets offer more data for less risk. Yet, the scientific value of returning to the surface of Venus is undeniable. Modern sensors, better materials, and advanced electronics could provide far more detailed measurements than the Soviet landers managed. New missions could study the mineralogy of rocks, search for signs of past water, monitor seismic activity to understand the planet's interior, and analyze atmospheric chemistry at ground level with precision that was impossible in the 1,970 seconds and 80 seconds. Some concepts for future Venus missions propose landers that could survive longer by using high-temperature electronics, or even balloons and airships that would float in the cooler upper atmosphere, avoiding the worst of the surface heat while still gathering valuable data. These ideas remain largely on paper, constrained by funding and the priorities of space exploration programs. Despite the long silence, Venus continues to exert a pull on the imagination of scientists and engineers. It is a planetary enigma, a twin that went wrong, a laboratory for studying extreme climates and atmospheric evolution. It is also a humbling reminder that proximity and similarity are no guarantee of habitability. The story of the Soviet campaign to land on Venus is inseparable from the larger story of human exploration. It is a chronicle of ambition and persistence in the face of brutal, unforgiving conditions. It is about engineers who watched their machines destroyed again and again, yet kept building better ones. It is about scientists who pieced together an understanding of another world from fragments of data, transmitted across millions of kilometers in the brief minutes before heat and pressure won. The images sent back by those landers, grainy, monochrome, and later in muted color, remain some of the most alien photographs ever taken. They show a place where the sky glows, but the sun is hidden, where rocks are baked to the edge of incandescence, and where the very air presses down with a weight that would crush a human body in seconds. They are windows into a world that exists in our solar system, close enough to reach, yet hostile enough to destroy almost anything we send. Building a machine to survive on Venus is not like building one for Mars or the Moon. On Mars, rovers face cold, dust, and thin atmosphere challenges, but manageable ones with proper engineering. On the Moon, there is no atmosphere at all, just vacuum, radiation, and temperature swings. Engineers have learned to handle these environments with insulation, batteries, and careful thermal management. Venus is fundamentally different. The environment is not just harsh, it is actively destructive in multiple compounding ways. The heat alone would disable most electronics. Standard silicon-based circuits begin to fail at temperatures well below what Venus offers. Solder melts, plastics degrade, and metals lose their strength. Even materials that seem tough on Earth become soft and pliable when baked at nearly 500 degrees Celsius for hours. Then there is the pressure. 90 times Earth's sea level atmosphere means every square centimeter of a lander's surface experiences crushing force. Seams, joints, and seals must be perfect, or the dense, corrosive air will infiltrate. Structural components must be thick and robust, adding mass and complexity. The lander cannot be light and elegant. It must be a fortress. The atmosphere itself is hostile beyond just pressure and heat. Sulfuric acid in the clouds, carbon dioxide that reacts with certain materials, and trace amounts of other corrosive compounds mean that exposed surfaces degrade rapidly. Even the descent through the atmosphere is a gauntlet, with friction heating the spacecraft and acidic droplets etching at any unprotected surface. Soviet engineers confronted these challenges with brute force solutions. They built thick hulls, used titanium pressure vessels to protect instruments, and wrapped everything in layers of insulation and shock absorption. They accepted that the landers would be heavy and that their operational lifetimes would be measured in minutes or hours, not days. The goal was not longevity, but survival long enough to transmit data. Each failed mission taught something. When early landers were crushed before reaching the surface, engineers learned that the atmospheric pressure was even more extreme than initial estimates suggested. When parachutes tore or melted, they realized that the lower atmosphere was so dense that traditional descent systems would not work. When transmissions cut off suddenly, they understood that thermal management was more critical than they had anticipated. These lessons were expensive. Each launch required a rocket, a spacecraft, months of flight time, and years of preparation. Each failure meant going back to the design table, identifying weaknesses, and building a new generation of hardware. But the iterative process worked. By the time the later Venera landers were descending, the Soviets had refined their approach to the point where survival, at least briefly, was almost guaranteed. The innovations they developed were not just about Venus. High-temperature electronics, pressure-resistant designs, and robust thermal management have applications in other extreme environments, from deep-sea exploration on Earth to missions to the outer planets where radiation and cold pose different but equally serious challenges. The engineering philosophy of designing for short-term survival in the worst possible conditions influenced later space missions and industrial technologies. Yet, the fundamental constraint remained. Venus destroys machines faster than engineers can protect them. Even with the best materials and designs available in the 1,970 seconds and 80 seconds, 2 hours was the limit. Beyond that, the heat penetrated too deeply. Circuits failed, and the landers went silent. The engineers had pushed the boundaries of what was possible with the technology of their era, but they had also reached a hard limit. The Soviet Venus program was never purely about science. It was entangled with the politics of the Cold War, with national pride, and with the desire to claim firsts in the space race. When the United States won the race to the moon, landing astronauts and planting flags, the Soviet Union needed other victories to maintain its image as a spacefaring superpower. Venus became one of those victories. The Soviets could say, truthfully, that they were the first to land a functioning spacecraft on another planet. They were the first to photograph the surface of Venus, the first to analyze its soil, the first to record its sounds. These achievements did not carry the same emotional weight as a human walking on the moon, but they were scientifically significant and symbolically important. The program also served a domestic purpose. Space exploration was a source of national pride, a demonstration of Soviet technological prowess, and a distraction from economic difficulties and political tensions. Success in space, even in the harsh environment of Venus, was proof that the Soviet system could compete with and sometimes surpass the West in cutting-edge fields. But politics is fickle. As the Soviet Union entered the 1,980 seconds, economic strain deepened. Resources that might have gone to space exploration were diverted to other needs. The space program continued, but priorities shifted. Missions to Venus, with their high costs and brief operational windows, became harder to justify. When the Soviet Union itself began to fracture and eventually collapsed, the Venus program ended not because the engineering problems were unsolvable, but because the political will and funding to solve them disappeared. NASA and other Western space agencies watched the Soviet Venus missions with interest, but chose not to follow the same path. The reasoning was straightforward. The scientific return per dollar spent on a Venus lander was low compared to other missions. Mars offered more hospitable conditions for long-term surface exploration. The outer planets and their moons presented opportunities to study diverse, exotic environments. Even returning to the moon seemed more appealing than wrestling with the inferno of Venus. There were also technical concerns. American spacecraft designs tended to prioritize longevity and reliability, philosophies that did not mesh well with the short, brutal timelines of a Venus landing. Building a lander that would function for an hour or two and then be destroyed felt, to many engineers and scientists, like a poor investment when the same resources could build a Mars rover that might operate for a decade. Orbital missions to Venus, on the other hand, were attractive. They could study the atmosphere, map the surface with radar, and monitor volcanic and weather activity without exposing delicate instruments to the crushing heat and pressure below. NASA's Magellan orbiter, launched in the late 1,980 seconds, mapped Venus in extraordinary detail, revealing its volcanic plains, towering mountains, and vast rift valleys. That mission provided more comprehensive surface data than any lander could, simply because it operated for years instead of hours. But orbital missions cannot answer every question. They cannot sample rocks, measure surface chemistry in fine detail, or test hypotheses about volcanic activity in real time. They are a view from above, useful but incomplete. To truly understand Venus, surface missions are necessary. The West recognized this, but concluded that the technology and cost were not yet justified by the science that could be gained. The last images from the surface of Venus are now more than 4 decades old. They show a static, barren landscape, frozen in time by the limitations of 1,980 seconds imaging technology. Since then, no new photographs have been taken from ground level. No new soil samples have been analyzed in situ. No new measurements of surface conditions have been made directly. This gap is significant. In the same period, Mars has been visited by multiple rovers, each more sophisticated than the last. We have driven across Martian plains, climbed hills, drilled into rocks, and analyzed the mineralogy and chemistry of the surface in extraordinary detail. We have watched dust storms unfold, tracked seasonal changes, and searched for signs of past water and potential life. Venus, by contrast, remains largely a mystery at the surface level. We know the broad strokes: hot, high pressure, volcanic, but the details are missing. Are there active volcanoes erupting now, or are they dormant? How does the surface interact with the atmosphere over time? What is the fine-scale mineralogy of the rocks? And what does it tell us about the planet's history? These questions cannot be answered from orbit. The gap also represents a missed opportunity. As climate science has advanced, Venus has become more relevant, not less. It is a natural laboratory for studying runaway greenhouse effects, atmospheric dynamics, and the long-term evolution of planetary climates. Understanding Venus better could inform models of Earth's climate and help predict how planets with thick atmospheres behave. Yet, without surface missions, much of that potential remains untapped. In recent years, interest in Venus has begun to stir again. Space agencies and private organizations have proposed new missions, some aiming to return to the surface, others planning to explore the atmosphere with balloons and aerial platforms. Advances in materials science, electronics, and thermal management have opened possibilities that were not feasible in the 1,970 seconds and 80 seconds. One concept involves high-temperature electronics based on silicon carbide and other materials that can function at temperatures far above what traditional silicon can handle. These components could, in theory, allow a lander to operate longer on the surface, gathering more data before succumbing to the heat. Another approach is to use cooling systems, actively managing the internal temperature of the lander to extend its operational life by minutes or hours. Aerial missions present a different strategy. The upper atmosphere of Venus, at altitudes around 50 to 60 kilometers above the surface, has relatively mild conditions, temperatures near room temperature and pressure similar to Earth's surface. A balloon or airship floating at that altitude could potentially operate for days or weeks, studying atmospheric chemistry, cloud dynamics, and even searching for potential biosignatures in the clouds. This approach avoids the worst of Venus's hostility while still providing valuable scientific data. NASA has announced plans for at least 2 missions to Venus in the coming decade, focusing on atmospheric studies and orbital mapping. Other space agencies, including those from Europe, India, and Russia, have expressed interest in Venus exploration as well. Private companies, driven by advances in aerospace technology and the lowering cost of launches, are also exploring concepts for Venus missions. These plans suggest that the long silence may be ending. Venus, the planet that destroyed every machine that touched it, may once again feel the presence of human-made hardware on its surface or floating in its skies. Beyond the science and engineering, Venus carries a philosophical weight. It is a cautionary tale about planetary fragility, about how worlds that begin with similar conditions can diverge into radically different fates. Earth and Venus started as siblings, but one became a cradle for life, and the other a furnace. The difference between them is, in cosmic terms, narrow a matter of distance, timing, and feedback loops. This divergence raises uncomfortable questions. If Venus, so similar to Earth in size and composition, could become uninhabitable, what does that say about the stability of our own world? How resilient is Earth's climate to disruption? At what point does a warming planet cross a threshold beyond which it cannot recover? These are not abstract questions. Human activity is changing Earth's atmosphere, increasing the concentration of greenhouse gases at a rate unprecedented in recent geological history. While Earth is not in immediate danger of becoming Venus, our distance from the Sun, our oceans, and our active carbon cycle provide buffers that Venus lacked. The mechanisms that drove Venus's transformation are the same ones that govern Earth's climate. Venus is a reminder that planetary climates can change in ways that are irreversible on human timescales. It is a monument to the power of feedback loops, to the danger of crossing tipping points, and to the importance of understanding the systems that keep a planet habitable. Some might ask why humanity should invest resources in studying a planet that is hostile, lifeless, and offers no prospect of colonization or resource extraction. The answer lies in what Venus represents: a laboratory for understanding planetary processes that apply everywhere, including here. Every piece of data from Venus, every measurement of temperature, pressure, and atmospheric composition, every image of its surface, every insight into its volcanic activity adds to our understanding of how planets work. That knowledge is not confined to Venus. It informs models of exoplanet atmospheres, helps scientists predict which distant worlds might be habitable, and sharpens our ability to understand Earth's own past and future. Venus is also a test of human capability. If we can build machines that survive even briefly on the most hostile planetary surface in the inner solar system, we prove that no environment is entirely beyond our reach. The engineering challenges of Venus push the boundaries of materials, science, robotics, and thermal management, driving innovations that have applications far beyond space exploration. And there is something more, something harder to quantify. Venus reminds us that the universe is not built for our comfort. It is a place of extremes, of beauty and terror in equal measure. By exploring Venus, we confront that reality directly. We reach out to a world that does not welcome us, that tries to destroy everything we send, and we persist anyway. That persistence, that refusal to be deterred by hostility, is part of what it means to be human. Behind every spacecraft that descended into the clouds of Venus were teams of engineers, scientists, and technicians who spent years of their lives on these missions. They calculated trajectories, tested materials, built prototypes, and watched their creations either succeed or fail in spectacular, distant silence. Each mission represented not just metal and electronics, but human effort, hope, and the sting of setback. The Soviet space program operated under immense pressure. Successes were celebrated publicly, paraded as proof of the superiority of the Soviet system. Failures were often hidden, buried in classified reports, or acknowledged only obliquely. Engineers who worked on the Venera program faced the weight of national expectation, the scrutiny of political leaders, and the knowledge that their work would be judged not just on scientific merit, but on its propaganda value. Yet, despite this pressure, or perhaps because of it, they produced remarkable achievements. They solved problems that had no precedent. They built machines for an environment that no one had directly experienced, using calculations and estimates that were, in the early years, little more than educated guesses. When those machines failed, they analyzed the data, learned from it, and tried again. The persistence was not just institutional, it was personal, driven by individuals who believed in the importance of the work. This human dimension is easy to overlook when discussing planetary exploration. The spacecraft become symbols, and the missions become historical footnotes. But every Venera lander that touched the surface of Venus carried with it the accumulated knowledge, skill, and determination of people who dedicated years to making it happen. Venus is, in many ways, the loneliest planet. Mars captures the imagination because it feels reachable, a place where humans might one day walk and build habitats. The Moon is close enough that we have already been there and left footprints. The outer planets and their moons are exotic, filled with subsurface oceans and strange chemistry that hint at the possibility of life. Venus offers none of that comfort. It is a planet where no human will ever stand, where no outpost will ever be built, where the very idea of setting foot on the surface is not just impractical but absurd. The environment is so hostile that even the most advanced spacesuits could not protect a person. The heat would kill in seconds, the pressure would crush, and the atmosphere would corrode and poison. This makes Venus a world that can only be experienced remotely, through instruments and data, through grainy photographs and columns of numbers transmitted across space. It is a place that exists for us only as abstraction, as knowledge rather than presence. And yet, it is real. Rocks sit on its surface, winds move through its air, and volcanoes may erupt beneath its clouds. It is a complete, functioning world, indifferent to whether we visit or understand it. That isolation gives Venus a strange, haunting quality. It is close enough to see in the evening sky, bright and beautiful, but far enough in character that it might as well be in another star system. It is a sibling that became a stranger, familiar in form, but alien in every meaningful way. For decades, the assumption about Venus has been absolute. Nothing lives there. The surface is too hot, the pressure too great, the chemistry too hostile. Life as we know it requires liquid water, moderate temperatures, and a stable environment. Venus offers none of these things. But in recent years, that certainty has been challenged, not at the surface but high in the atmosphere. In the cooler, more temperate layers of clouds, conditions are less extreme, temperatures hover around comfortable levels, and pressures are manageable. Liquid droplets of sulfuric acid float through the air, creating a strange but potentially habitable niche. Some scientists have speculated, controversially, that microbial life could exist in those clouds. Microbes on Earth can survive in acidic environments, and some can remain dormant in harsh conditions for long periods. If life ever existed on Venus during a time when the surface had water, it is conceivable, though far from proven, that some organisms could have adapted to survive in the atmosphere as the surface became uninhabitable. In 2020, researchers announced the detection of phosphine, a gas that on Earth is primarily produced by biological processes, in the atmosphere of Venus. The announcement sparked intense debate. Phosphine in Venus's clouds could be a biosignature, evidence of microbial life floating in the skies. Or it could be the result of unknown chemical reactions, geological processes, or even an error in the data analysis. Subsequent studies have questioned the detection, suggesting that the signal might have been a misinterpretation or that other explanations are more plausible. The debate remains unresolved, and the question of whether Venus harbors any form of life, however simple and unlikely, remains open. Answering it will require more missions, more measurements, and direct sampling of the atmosphere. The possibility, however remote, that life exists on Venus changes the narrative. The planet is no longer just a dead, hostile rock. It becomes a place where biology might have found a way to persist, a world that could teach us about the limits of life and the environments where it can survive. Even as attention shifts to atmospheric missions and the faint possibility of life in the clouds, the surface of Venus retains its pull. The images sent back by the Venera landers, despite their age and limited quality, remain powerful. They show a landscape that is both alien and strangely mundane: rocks, dust, a low horizon. It is not the dramatic scenery of towering cliffs or vast deserts. It is, in many ways, unremarkable, and yet the context transforms it. Those rocks sit under a sky that glows with diffuse light filtered through sulfuric acid clouds. The air pressing down on them weighs as much as an ocean. The temperature is hot enough to make some metals glow. The landscape is static, not because nothing happens, but because the conditions are so extreme that change occurs on timescales. We rarely consider rocks slowly deforming under heat and pressure, surfaces etching away under chemical attack. The photographs also remind us of how little we have seen. Each Venera lander captured only a narrow field of view, a tiny patch of ground around the landing site. Venus has a surface area comparable to Earth's landmass, yet we have detailed images of only a few square meters. The rest is known only through radar mapping from orbit, which provides topography and structure but not texture, color, or detail. There are mountains on Venus taller than any on Earth. There are vast plains of lava stretching for thousands of kilometers. There are rift valleys, volcanic domes, and strange features with no clear analogs on our planet. We can see these in radar maps, but we have never looked at them up close. We have never stood at the base of a Venusian mountain, never watched lava flow across its surface, never seen the play of light through its thick atmosphere at different times of day. If new missions return to the surface of Venus, they could answer questions that have lingered for decades. High-resolution cameras, modern spectrometers, and advanced analytical instruments could study the composition of rocks in far greater detail than the Venera landers managed. They could determine not just what minerals are present, but how they formed, what processes shaped them, and what they reveal about Venus's geological history. Seismometers on the surface could detect Venusquakes, providing insights into the planet's internal structure and the movement of its mantle. Are there tectonic processes at work beneath the crust? Or is Venus's interior too sluggish to drive the kind of plate movement we see on Earth? Does the planet experience large-scale volcanic eruptions? And if so, how often? Long-term monitoring of surface conditions could reveal changes over time. Does the temperature vary with location or time of day? Are there weather patterns at ground level? Movements of the thick air that could be considered wind in the traditional sense? Do volcanic eruptions alter the local environment, releasing gases or altering the landscape in ways that can be measured? Aerial platforms floating in the upper atmosphere could study the clouds directly, sampling their chemistry and searching for organic molecules or other compounds that might indicate biological activity. They could observe atmospheric dynamics, track the super-rotating winds, and monitor changes in cloud composition and structure over days or weeks. These missions would not make Venus habitable or accessible to humans, but they would make it knowable. They would fill in the gaps left by decades of silence, transforming Venus from a vague threat and cautionary tale into a fully understood world with a documented history and character. One of the obstacles to renewed exploration of Venus is public interest, or the lack of it. Space missions depend on funding, and funding depends on public support or at least political will. Mars captures attention because it feels like a destination. Images of Martian landscapes, with their dusty hills and ancient riverbeds, evoke a sense of possibility. People can imagine rovers rolling across those plains, and eventually, humans walking there. Venus does not inspire the same kind of imagination. It is too hostile, too alien. The images from its surface, while scientifically valuable, do not have the visual appeal of a Martian sunset or the rings of Saturn. The idea of exploring Venus does not come with dreams of colonization or visions of a second home for humanity. It is exploration for its own sake, for the sake of knowledge, and that is a harder sell. Yet, this is precisely why Venus matters. Not every mission needs to be about human expansion or resource extraction. Some missions are about understanding the universe, about answering fundamental questions regarding how planets work and why they evolve the way they do. Venus is a test case in planetary science, a natural experiment that played out over billions of years. Studying it is not about finding a new place to live. It is about learning what makes a planet livable in the first place. Communicating this importance to the public is a challenge. It requires shifting the narrative from exploration as conquest or settlement to exploration as discovery and understanding. It means emphasizing that the lessons learned from Venus apply to Earth, that studying a runaway greenhouse on another world helps us protect the climate on our own. The Soviet Venera missions remain, even decades later, a remarkable achievement in the history of space exploration. They were the first to successfully land functioning spacecraft on another planet. They returned the first photographs from the surface of an alien world. They gathered data under conditions more extreme than any other planetary mission had faced. Their legacy is not just in the data they collected, but in what they demonstrated about human persistence and ingenuity. The engineers and scientists behind those missions faced failure after failure, yet they continued. They refined their designs, learned from mistakes, and pushed the boundaries of what was technically possible. They did this under political pressure, with limited resources compared to their American counterparts, and often with less public recognition. The Venera program also set a precedent. It showed that even the most hostile environments in the solar system are not entirely beyond reach. If machines could survive on Venus, even briefly, then no planetary surface is completely inaccessible. This mindset has influenced later missions to extreme environments, from the depths of Titan's atmosphere to the radiation-drenched surface of Jupiter's moon Europa. But the legacy is incomplete. The Venera program ended not because it had answered all the questions, but because the resources and political will to continue it disappeared. The knowledge it gained was foundational, but limited. Venus remains, in many ways, unfinished business, a world explored just enough to reveal how much more there is to learn. Venus is one piece of a larger puzzle. Understanding it helps scientists build a comprehensive picture of how rocky planets form, evolve, and respond to different conditions. Each planet in the solar system is a data point, a variation on the theme of planetary development. Mercury, baked by the sun and stripped of most of its atmosphere, shows what happens when a planet is too close and too small. Mars, cold and dry, demonstrates the fate of a world that lost its magnetic field and much of its atmosphere. Earth, stable and habitable, sits in a narrow range of conditions that allow liquid water and life. Venus, close to Earth in size and position but radically different in outcome, reveals how sensitive planetary climates are to small changes in initial conditions. This comparative approach to planetary science has reshaped our understanding of Earth. By studying other worlds, scientists have learned to see Earth not as a fixed, unchanging stage, but as a dynamic system shaped by complex interactions between its atmosphere, oceans, geology, and life. Venus in particular has been crucial in understanding greenhouse effects, atmospheric dynamics, and the long-term consequences of volcanic outgassing. As astronomers discover thousands of exoplanets orbiting other stars, many of them rocky worlds similar in size to Earth and Venus, the lessons from our solar system become even more important. Which of those distant worlds might be habitable? Which might be hellish, like Venus? Without understanding Venus, scientists cannot confidently answer those questions. Every measurement from Venus, every piece of data about its atmosphere and surface, helps refine models that predict the conditions on planets we will never visit but desperately want to understand. To appreciate what the Venera landers accomplished, it helps to understand the specific engineering solutions that kept them alive, even briefly, on the surface of Venus. These were not elegant spacecraft. They were brutal, pragmatic machines designed with a single-minded focus. Survive long enough to transmit data, then accept destruction. The outer shell of a Venera lander was built from thick steel or titanium, designed to withstand the atmospheric pressure during descent and on the surface. Inside that shell, critical instruments were housed in spherical pressure vessels, a shape chosen because it distributes stress evenly and resists crushing better than any other geometry. These inner spheres were surrounded by layers of insulation to slow the penetration of heat from the outside environment. Cooling systems were minimal, relying mostly on passive heat sinks, masses of material that could absorb thermal energy for a limited time. Active cooling, like refrigeration, would have required power and added complexity, and even then, it would only buy minutes. The philosophy was to accept that the lander would eventually overheat, but to delay that moment long enough to complete the mission. Power came from batteries, pre-charged before launch and designed to function at high temperatures. Solar panels were useless on Venus, where thick clouds block direct sunlight and the surface receives only a dim, diffuse glow. The batteries had to provide enough energy for communications, cameras, instruments, and any mechanical systems like drills or soil samplers, all while being slowly cooked by the ambient heat. Communications were another challenge. Transmitting data from the surface of Venus back to Earth required a radio signal strong enough to punch through the thick atmosphere and cross tens of millions of kilometers of space. The landers used high-gain antennas and powerful transmitters, but even then, the data rates were slow by modern standards. A single image might take many minutes to transmit, line by line, each precious second of operation devoted to sending back as much information as possible before the inevitable failure. Descent was perhaps the most critical phase. The lander had to survive entry into the atmosphere at thousands of kilometers per hour, shedding speed through a combination of aerodynamic drag and heat-resistant shielding. As it slowed, it deployed parachutes or aerodynamic braking structures to further reduce speed. In the lower atmosphere, where the air is as thick as water, the lander could rely on drag alone to slow its fall, dropping the parachute to avoid tangles or failures. The final impact had to be absorbed without breaking critical components. The shock-absorbing landing ring, with its metal teeth and crushable structures, distributed the force of the collision across a wide area. Inside, instruments were cushioned and mounted on springs or dampers to reduce the jolt. Even so, landings were violent, and not every system survived intact. When a Venera lander fell silent, it did not explode or dramatically fail. It simply stopped responding. The heat penetrated deep enough to disable circuits. Chemical reactions within batteries slowed and then ceased. Solder joints weakened, connections broke, and the delicate electronics that had functioned against all odds finally succumbed. The lander remained on the surface, a metal husk slowly baking in the relentless heat. Over days, weeks, and years, it would continue to degrade. Seals would fail, the atmosphere would seep in, and corrosive gases would attack internal components. The outer shell, exposed to sulfuric acid and extreme temperatures, would etch and corrode. Eventually, the lander would become little more than a deformed lump of metal and ceramic, indistinguishable from the rocks around it. Somewhere on the plains of Venus, these silent relics still sit. A dozen or more Soviet landers scattered across different landing sites, each one a monument to human ambition. They are the only human-made objects on the surface, and they will remain there for eons, slowly dissolving into the landscape. There are no winds strong enough to bury them, no water to erode them, no life to reclaim them. They simply wait, forgotten by all but historians and scientists, slowly being reclaimed by the planet they came to study. Every year that passes without a new mission to the surface of Venus represents a lost opportunity. The technology to build better landers exists. Materials that can withstand higher temperatures for longer periods have been developed. Electronics that function at temperatures well above what silicon can handle are available. Advances in miniaturization mean that instruments can be smaller, lighter, and more capable than those carried by the Venera missions. Yet, missions are not built on technology alone. They require funding, political support, and competition for limited resources within space agencies. Mars missions, lunar exploration, asteroid studies, and outer solar system probes all compete for the same budgets. Venus, with its hostile reputation and lack of public appeal, often loses that competition. The cost of this inaction is not just scientific, it is cultural. Venus becomes a forgotten world, a footnote in the history of exploration rather than an active frontier. The lessons it could teach about planetary climates, volcanic activity, and atmospheric evolution remain unlearned. The engineering challenges it presents, which could drive innovation in materials, science, and robotics, go unmet. There is also a generational dimension. The engineers and scientists who worked on the Venera program are aging. Their knowledge, experience, and institutional memory are fading. If new missions to Venus are delayed too long, that continuity will be lost, and future efforts will have to rediscover lessons that were already learned decades ago. One of the most compelling reasons to study Venus now rather than later is its relevance to Earth's climate. As human activity increases the concentration of greenhouse gases in Earth's atmosphere, the risk of triggering feedback loops that amplify warming becomes more pressing. Venus is the ultimate example of what happens when those feedbacks spiral out of control. Understanding the mechanisms that drove Venus's transformation, how water was lost, how carbon dioxide accumulated, how the surface temperature stabilized at its current extreme level, provides crucial data for climate models. These models are used to predict how Earth's climate will respond to increasing greenhouse gas concentrations and how close we might be to dangerous tipping points. Venus also offers insights into the role of volcanism in atmospheric composition. On Earth, Volcanic eruptions release carbon dioxide and sulfur compounds, temporarily affecting climate. On Venus, volcanic activity may have played a major role in creating the thick, carbon-rich atmosphere. By studying Venus, scientists can better understand the long-term interplay between geology and climate, and how volcanic activity on Earth might influence our atmosphere over millions of years. The parallels are not exact. Earth has oceans, a magnetic field, and a different distance from the Sun, but the physics is the same. Greenhouse gases trap heat. Feedback loops amplify changes. Water vapor, carbon dioxide, and temperature are linked in complex ways. Venus is a natural laboratory where these processes have played out to an extreme conclusion, and studying it helps refine our understanding of the same processes on Earth. The next generation of Venus exploration will likely involve international collaboration. No single space agency has a monopoly on interest in Venus, and the costs and technical challenges make shared missions attractive. NASA, ESA, Roscosmos, ISRO, and other agencies have all expressed interest in Venus, and some have proposed joint missions that would combine resources and expertise. International collaboration brings advantages beyond cost sharing. Different agencies have different strengths. Some excel in orbital missions, others in lander design, still others in atmospheric analysis. By combining these strengths, missions can be more ambitious and scientifically productive than any single agency could achieve alone. There are also diplomatic and symbolic benefits. Space exploration, particularly of scientifically important targets like Venus, can serve as an arena for cooperation in a world often divided by politics and conflict. Joint missions build relationships, share knowledge, and demonstrate that humanity can work together to answer fundamental questions about the universe. However, collaboration also introduces complexity. Coordinating between agencies with different timelines, budgets, and priorities is difficult. Technical standards, communication protocols, and mission design philosophies may differ, requiring compromise and careful planning. The history of international space missions includes both great successes and frustrating delays, and Venus missions will face the same challenges. Among the more speculative ideas for exploring Venus is the concept of aerial habitats, floating platforms, or even cities suspended in the upper atmosphere. At altitudes where temperatures and pressures are Earth-like, such structures could theoretically support human life with far less infrastructure than would be needed on the surface. These habitats would float using the buoyancy provided by the thick Venusian atmosphere. Balloons filled with breathable air, mostly nitrogen and oxygen, would actually float in the carbon dioxide atmosphere of Venus, much like a helium balloon floats in Earth's air. The platforms could house scientific instruments, laboratories, and potentially even small crews of researchers. The concept is not pure fantasy. The engineering challenges are significant, but not insurmountable with current technology. The main obstacles are logistical, getting materials and people to Venus, constructing the habitats, and ensuring long-term sustainability. Still, as a long-term vision, it represents a way for humanity to establish a presence at Venus without confronting the lethal surface. If you're enjoying this journey into the nature of Venus and the extremes of planetary exploration, consider subscribing to our channel, Broken Zach, so you don't miss what comes next. Floating habitats could also serve as bases for exploring the lower atmosphere and surface. Drones and robotic probes could be deployed from the platforms, descending into the hotter, more dangerous layers to gather data and return, or, if designed for single use, simply transmit their findings before being destroyed. This tiered approach to exploration would allow for sustained study of Venus in ways that surface missions alone cannot provide. One of the most intriguing unanswered questions about Venus is whether it is still volcanically active. The surface shows clear signs of past volcanism, vast lava plains, volcanic domes, and features that look like they formed from molten rock. But is this ancient history, or is Venus erupting today? Orbital observations have provided tantalizing hints. Some studies have detected variations in sulfur dioxide levels in the atmosphere, which could indicate fresh volcanic outgassing. Others have observed bright spots on the surface that might be recent lava flows, still warm enough to emit infrared radiation detectable from space. But these observations are ambiguous, and without direct measurements from the surface or sustained monitoring, it is impossible to be certain. Confirming active volcanism on Venus would be a major discovery. It would mean that the planet's interior is still geologically dynamic, that heat from the core is driving processes that reshape the surface. It would also have implications for the atmosphere, as volcanic eruptions release gases that contribute to the thick, corrosive blanket surrounding the planet. Surface missions equipped with seismometers could detect Venus quakes, which would provide evidence of internal activity. Cameras and spectrometers could watch for changes over time, looking for fresh lava flows or variations in surface temperature that indicate recent eruptions. Long-duration aerial platforms could monitor the atmosphere for sudden increases in volcanic gases, correlating them with surface activity. There is an irony in the appearance of Venus. From Earth, it is one of the most beautiful objects in the sky, bright, steady, and serene. Ancient cultures worshipped it as a goddess of love and beauty, and even today it is often called the evening star or morning star, a beacon of light in the twilight. But up close, Venus is anything but serene. Its surface is a hellscape, its atmosphere toxic and crushing, its clouds made of acid. The contrast between appearance and reality is stark, a reminder that the universe does not care about human aesthetics or expectations. Yet, there is a strange beauty in the Venera images too. The rocks, lit by the dim, filtered light that reaches the surface, have a somber, alien quality. The landscape is barren, but it is real, a place that exists, utterly indifferent to human presence. The photographs capture a moment of connection between Earth and another world, a brief window into an environment no human eye will ever see directly. This aesthetic dimension of exploration is often overlooked. We talk about science, engineering, and practical benefits, but part of the drive to explore is simply the desire to see, to know what other worlds look like, to expand the range of human experience, even if only vicariously through machines. Venus teaches humility. It reminds us that not every world is welcoming, that the universe contains environments far beyond human tolerance. It shows that proximity and similarity are not guarantees of accessibility. Earth and Venus are neighbors, almost twins. Yet one is a cradle of life and the other a furnace. This lesson applies beyond planetary science. It speaks to the limits of human control and the importance of respecting systems we do not fully understand. Venus transformed not through malice or intent, but through the interplay of physical processes that, once set in motion, could not be stopped. The planet crossed a threshold, and there was no going back. Earth, too, is subject to thresholds and feedback loops. We do not know exactly where they lie or how close we are to crossing them. Venus is a warning, a demonstration of what lies on the other side of a runaway climate. It is a reminder that planets are not stable, unchanging stages, but dynamic systems that can shift from one state to another, sometimes irreversibly. The humility that Venus teaches is not about giving up or accepting defeat. It is about recognizing the complexity of the systems we study and the responsibility that comes with influencing them. It is about understanding that knowledge is hard-won, that nature does not yield its secrets easily, and that exploring the universe requires persistence, creativity, and a willingness to accept failure as part of the process. The surface of Venus is silent now, in the way that only a place devoid of human presence can be. The last transmissions from the Venera landers came decades ago, their voices fading into static as the heat and pressure claim them. Those final moments of operation, when instruments strained against the environment and antennas fought to send data across millions of kilometers, have become historical artifacts. The machines are gone, but the data they sent remains, archived and studied, a fragmentary record of a world that resists being known. In that silence lies a question that applies to all exploration. Why do we reach for places that do not want us? Venus offers no resources we need, no refuge we could use, no promise of life or beauty in the conventional sense. It is hostile in ways that make even the harshest deserts on Earth seem inviting. And yet, humanity sent probe after probe, built lander after lander, and poured resources and effort into touching a world that destroys everything we send. The answer is not practical. It is something deeper, tied to the nature of curiosity itself. We explore because not knowing is intolerable. We reach for Venus because it is there, because it challenges us, and because understanding it means understanding something fundamental about the universe and our place within it. The drive to explore is not always rational, and it does not always yield immediate benefits. but it is persistent, and it shapes the trajectory of human civilization. One of the uncomfortable truths about the Venera program is how easily its knowledge could have been lost. The Soviet Union collapsed, archives were scattered, and institutional memory faded. Some of the original data from the missions was stored on obsolete media, requiring effort to recover and preserve. The engineers and scientists who built and operated the landers have aged, and many have passed away without fully documenting their work. This fragility is not unique to Venus missions. Much of the data and knowledge from early space exploration exists in precarious states: old magnetic tapes, paper records stored in boxes, memories held by individuals rather than institutions. The pace of technological change means that the formats and systems used to store information decades ago are often incompatible with modern tools, requiring dedicated efforts to migrate and preserve. For future Venus missions, this is a lesson. The data gathered is valuable not just in the moment, but for decades and centuries to come. Ensuring that it is stored in accessible, long-term formats, that the context and methods are documented, and that the knowledge is shared widely is as important as the missions themselves. Exploration is not just about discovery. It is about preserving what is discovered so that future generations can build on it. When the next lander touches down on Venus, and it will happen, eventually it will not be alone. It will carry with it the legacy of the Venera program, the lessons learned from decades of failure and success, and the accumulated knowledge of planetary science. It will be built with materials and technologies that did not exist in the 1,970 seconds, capable of surviving longer and measuring more than its predecessors. That lander will see a landscape that has not been photographed in over 40 years. It will capture images with resolutions far beyond what the Venera cameras could achieve, revealing textures, colors, and details that were invisible before. It will analyze rocks with spectrometers that can identify minerals down to trace elements, telling the story of how those rocks formed and what processes shaped them. It will measure seismic activity, listening for the subtle vibrations that indicate a geologically active planet. It will monitor atmospheric conditions at ground level, tracking how temperature, pressure, and composition change over time. It may even watch for volcanic eruptions, capturing the first direct observations of active geology on Venus. And when it falls silent, as all Venus landers must, it will leave behind more than just data. It will leave a marker, a sign that humanity has not given up on understanding this difficult, dangerous world. It will be another step in a long, interrupted journey toward comprehending what Venus is and what it means. Venus is not just a planet. It is a story about divergence, about how small differences in initial conditions can lead to radically different outcomes. It is a laboratory for studying climate, geology, and atmospheric dynamics under extreme conditions. It is a warning about the fragility of habitable environments and the power of feedback loops. It is a monument to human persistence, to the willingness to confront hostile environments and wring knowledge from them despite the cost. But perhaps most importantly, Venus is a reminder that the universe is vast and indifferent. It does not care whether we explore it or understand it. It does not offer easy answers or comfortable truths. It is what it is, beautiful and terrible, fascinating and hostile, filled with wonders and dangers in equal measure. Exploring Venus means confronting that indifference and asserting, through the act of exploration itself, that understanding matters, that knowledge has value, that the effort to reach beyond our immediate surroundings, to see and measure and comprehend, is worth the cost and the risk. It is easy to talk about spacecraft and missions as abstract entities, but every one of them is the product of human labor and creativity. Behind the Venera landers were machinists who fabricated components, chemists who developed heat-resistant materials, programmers who wrote control software, and engineers who integrated thousands of parts into a functioning whole. There were mission planners who calculated trajectories, communications specialists who designed antennas and receivers, and scientists who decided what instruments to carry and what measurements to take. There were technicians who tested every system, managers who coordinated the work, and political leaders who decided whether to fund the missions. Each of these people contributed to the exploration of Venus, often without recognition. Their names do not appear in history books, and their individual efforts are lost in the collective narrative of the Venera program. But without them, there would be no landers, no photographs, no data. They are part of the story, even if they remain invisible. This is true of all exploration. The astronauts and cosmonauts who fly into space are celebrated, but they depend on thousands of unseen people who make their missions possible. The rovers that explore Mars are icons, but they were built by teams whose names we will never know. The act of exploration is communal, a shared effort that transcends individuals. In the sweep of history, the Venera missions will be remembered not for their political context or their propaganda value, but for what they achieved scientifically. They were the first to land on another planet. They revealed what Venus is really like beneath its clouds. They demonstrated that even the most hostile environments in the solar system are not entirely beyond reach. Decades or centuries from now, when Venus has been explored more thoroughly, when landers survive for days instead of hours, when aerial platforms drift through its clouds gathering data, the Venera program will be seen as the beginning, the first crude, heroic attempts to touch a world that did not want to be touched. Future historians will look back at those grainy photographs and wonder what it was like to see them for the first time, to realize that the surface of Venus was not jungle or ocean, but rock and dust, baking under a dark sky. They will study the engineering solutions, the titanium spheres, the shock absorbers, the aerodynamic braking, and see the ingenuity of people working with limited tools and knowledge. And they will recognize, perhaps more clearly than we can now, that the exploration of Venus was not just about Venus. It was about humanity testing its limits, asking how far it could reach and what it could learn. It was about refusing to accept ignorance, even when the cost of knowledge was high. The story of Venus exploration is not over. It is paused, suspended in a decades-long silence that may finally be ending. New missions are being planned, new technologies developed, new questions formulated. The world that the Venera landers briefly touched is about to be visited again, studied more deeply, understood more fully. But even when those missions fly, even when new data streams back from the surface and atmosphere, Venus will not be fully known. There will always be more to learn. More mysteries to unravel, more questions that arise from the answers we find. That is the nature of exploration. It is a journey without a final destination, a process of continual discovery and refinement. Venus will continue to orbit the sun, indifferent to our attention. Its surface will continue to bake, its atmosphere to churn, its volcanoes to erupt or lie dormant. It is a world unto itself, complete and self-contained, existing whether we study it or not. Yet, by reaching out to Venus, by sending our machines and our instruments, by gathering its light and measuring its heat, we make it part of our story. We bring it into the realm of human knowledge and understanding. We transform it from a point of light in the sky into a place, a world with history and character, with lessons to teach and secrets to reveal. In the end, the exploration of Venus is a choice. It is not necessary for survival. It does not provide immediate economic benefits. It does not solve pressing problems on Earth. It is a choice to value knowledge for its own sake, to believe that understanding the universe is worth the effort and expense. That choice reflects something fundamental about human nature. We are curious. We ask questions. We seek to understand not just what is immediately around us, but what lies beyond our reach. We look at a bright point in the evening sky and wonder what it is, and then we build machines to go there and find out. The Soviet engineers who built the Venera landers made that choice. The scientists who analyzed the data made that choice. The political leaders who funded the missions, however mixed their motives, made that choice. And in making it, they contributed to a legacy of exploration that stretches back to the first humans who ventured beyond their immediate surroundings and forward to future generations who will continue to reach for distant worlds. Venus is one chapter in that larger story. It is a difficult chapter, filled with failures and setbacks, but also with persistence and achievement. It is a chapter that reminds us that exploration is not always triumphant, that knowledge is hard-won, and that the universe does not yield its secrets easily. From Earth, Venus remains what it has always been, a bright wanderer in the sky, visible for a few hours after sunset or before dawn. Most people who see it do not think about the furnace beneath its clouds, the crushing pressure at its surface, or the silent Soviet landers slowly corroding in the heat. They see a star, beautiful and distant. But for those who know the story, who have seen the photographs and studied the data, Venus is transformed. It is no longer just a light in the sky. It is a place, real and tangible, with rocks and dust and sky. It is a world that humans have touched, however briefly, and from which we have wrested fragments of understanding. That transformation from light to place, from mystery to knowledge, is what exploration accomplishes. It changes how we see the universe. It makes the distant familiar and the abstract concrete. It connects us to worlds we will never visit, building bridges of understanding across the void. Venus will always be hostile. It will always resist our attempts to study it, but it is no longer entirely unknown. We have been there. We have seen its surface, measured its air, touched its rocks. And in doing so, we have made it part of human experience, woven it into the story of our species. The bright star in the evening sky is no longer just Venus. It is also a monument to curiosity, persistence, and the drive to understand. It is a reminder of what we can achieve when we choose to explore, even when the journey is difficult and the destination is hostile. And it is a question, hanging in the darkening sky, waiting for the next generation to answer. What else is out there, waiting to be discovered? What other worlds lie beyond our reach, holding secrets and lessons we have not yet imagined? The silence from Venus is not an ending. It is a pause, a breath before the next attempt. Somewhere, engineers are designing new landers. Scientists are formulating new questions. Planners are mapping out trajectories and timelines. The journey continues, interrupted but not abandoned, difficult but not impossible. Venus waits, as it always has, bright and beautiful and deadly, for the next visitors from Earth. If you enjoyed this video, watch this one too. It's a great one, and we'll see you in the next video.